Welcome back to the hyperbolic coding chamber. We are back once again. Today we have returned. Mark, Susan, all the top tech CEO and billionaires have allowed us to meet today. They've got me captive. To be honest, the HCC is under attack, and I'm now a puppet for the tech conglomerate. So that's kind of where we're at. Fortunately, though, there's a silver lining. Yesterday we were able to solve for some. So I'm going to be honest, today is probably just going to be us trying to understand the solution. But it turns out, and maybe this has something to do with my thought process, I worked on this problem, and it turns out the first solution we tried worked. But for some reason, I thought that meant my entire solution was wrong, so I should have just tried to optimize that. That's a lesson that took us 2 weeks to learn, so hopefully it won't take us that long next time. But I think we're just going to try and read the solution and figure things out. That being the case, we're a little bit strapped for time today, so I think I'm just gonna jump straight. So I'm gonna say we'll do 25. Actually, we always do a shorter session on Friday. I was gonna do 20, and we're just gonna be pretty much understanding this. So pretty much top down. I think we worked on this problem for so long I could probably regurgitate exactly what the problem is asking for. Basically, we're given a list of numbers up to n, and we should return a list of numbers. We're given a list of numbers n as well as a target. We're basically looking for 4 unique quadruplets. We're looking for a unique quadruplet that sums up the target. The indices that the indices that these numbers are created from should be unique. Similarly, the 4 quadruplets themselves must also be unique. That being the case, the version we wrote is actually sort of ghetto. We pretty much did n squared operations to pretty much generate every possible two sum pair. Then after taking those 2 sum pairs, we put them into an map. This map basically maps a sum to the indices that can create that sum. From there, we iterate through all sums, all 2 number sums, right? And we'll check if the complement of that number to get the target exists in the map. If it does, we should pretty much check all the indices against all the other indices, right, to see how many different ways we can this sum, or how many different ways we can reach the target. Then we layered like 3 edge cases on top of it and optimism. I don't know what the time complexity is, but it's probably pretty crazy because the algorithm takes 7 seconds. I'm trying to figure out why. It's not even a premium solution. We have this version, that Python version, 140 million for n minus sum, n is greater than or equal to. So core is the fast 2-pointer to solve 2 sum, and recursion to reduce n sum to 2 sums. Some optimization was made knowing the list. They take the numbers, they sort it, results equal to empty array, and then they recursively seem to call a function called find n array of numbers, a target, the goal size, which is n. Actually looks like this. Oh, I see. This works for n sum. Only when n is greater than or equal to 2. Results. So if the length of n less than n, or n is less than, okay, it has to be it's saying if length of nums is less than n, or n is less than 2, return. So, okay. Here we're going to solve two. N is equal to 2, then left equals 0, and right equals 1. While left is less than right, we'll check if num sub L plus num sub R equals target. We'll do results dot. Well, the target, we're solving for 2. Okay. Oh my god. No, I don't think I got it. Results dot append results plus num sub L, num sub right. So we append the result. This is for solving two sums. Right, L plus equals R. Right, minus less than R. While L is less than R, which it is, and num sub L equals num. Oh, okay, we want to skip. Right, we want to skip numbers that are same because the array is sorted, so we can that we want to do the same, right? Then we'll say if it's less than target, then we'll. Right, if it's less than target, the closest way we can increment it without going over is by increment, bringing in the next small number. Otherwise, right, same. If we're over it, the next way we can bring it down is by removing to the next smallest number. This is for two sum. This is not two sum. Magic seems to be in here. For I in range 0 to length of nums. Say we have 5 numbers. Let's just say we have 5 numbers in the array, and our n is 4. We do length of nums, which is 5 minus 4 gives us 1 plus 1 gives us 2. If target is less than num sub I times, or target is greater than the last element, okay? Yeah, I don't understand. Saying recursively reduce it for I in range L to R plus 1. If I equals L, or I is greater than L, sum sub I minus 1.
Mm.
We sort the array, go from I to iterate over all the numbers. Target 3 is target. Right, then we j equals I plus size. Target 2, target 3. Okay. Mm. So we sort here, go through all the numbers, go from I plus 1 to n, right? So squared, goal is target minus number I minus j. We see the beginning is equal to j plus minus n minus 1. Beginning is plus num sub n is less egg plus else equals it, and just append them all together. I guess they would be sorted this sort. Egg plus minus equals 1. But I thought the 2-pointer version wasn't not capable of all 4 numbers and making them exhaustive for a given number, and exhaustive find all the versions would add up to it. No, I don't see how it is. Correct. Oh, num sub egg plus num sub n, then we add 1 to it, and then we keep going. So as we go over and above, we end up adding everything. I think I have to look at this one again, but this one seems to make sense. Oh God, LeetCode is a mess, man. So I think we'll stop there for today, and tomorrow we'll probably turn to the regular